Hi, I'm Nick Witham. I'm going to be talking about artificial muscles today. The type of artificial muscle I research in my lab is twisted coiled polymer muscles. It's a pretty self-explanatory name. They're just polymers that are twisted and coiled. They're thermally anisotropic, and when you heat them, they contract. More specifically, what I'm going to be talking about is computer vision to analyze and measure the geometries of said muscles. Okay, but before I do that, since I'm a biomedical engineer, I want to start with the patient need. Specifically, I'm designing these muscles for prosthetic applications and for assistive device applications. While prosthetics are highly advanced and are very expensive, they don't do everything that people intend. And as you've probably seen on several posters today, the abandonment rate's about 50% for upper limb. So things could definitely be improved. This gentleman right here, his name is Johnny Matheny, and he's widely considered to be the world's most advanced cyborg. That's how he self-describes, so I'm going to describe him as such. But they describe him that way because his arm cost $1.5 million to assemble. So, you know, this is not a commercially available prosthetic, but even at that upper end, there's still room for improvement.
How do you want people in the future to feel when they're wearing a prosthetic?
Any way to get volume from this?
It worked 8 hours ago when I tested that.
All right.
Can you unmute me?
Yeah. Well, you have to do it yourself. Like your audio.
Okay.
I want to get rid of several of those. I don't know if I'm going to be any better than you are. That's.
All right.
Yeah,
Well, it's subtitled for a reason.
How do you want people in the future to feel when they're wearing a prosthetic?
I want them to feel proud. I want them to feel like they're back as a natural community using their natural community. I want them to be able to wear their like their natural being. I want them to be able to feel like their natural being. Whether the upper extremity, lower extremity, they will be able to touch the ground and feel the ground.
If you notice, he said the word natural three times. He wants prosthetics to feel natural. And even at the price tag of $1.5 million, it doesn't pass the buck. So yes, his prosthetic is advanced. Yes, it moves better than any other prosthetic, except for maybe Greg Clark's prosthetic. But there's still room for improvement. Anything we can do to improve the natural feel and the holistic nature of prosthetics would improve the field and people's lives. So back to the topic. My artificial muscles, they're made from yarn. They're made from twisted coiled yarn. When you heat them up, they want to untwist. They also generate a torque if you don't allow them to untwist. When you coil that yarn, it causes a contraction. So when a spring, just a regular steel spring, is extended, it generates a torque. So since these things manifest their things that we measure and a few geometric things that we control. So what we can manufacture and control are the twists, so the number of turns in the fiber, and the writhe, the number of turns in the yarn. What we can measure and what the geometry we care about are the bias angle and the spring index. Bias angle is a number usually less than 1, which is the relationship of the nominal coil diameter, so center to center, over the fiber diameter. So it controls how fat your coil is. The other factor we look at is bias angle. It is generally a factor of linear density. So if you start with a fiber of a certain length, a bias angle will make a certain height. And it is the angle at which it measures the opposite, which is the distance between turns or pitch, over the circumference. So if you were to unspool that fiber, it would take the path of the hypotenuse. What we did is we extruded the filament at 0.3 millimeters. We twisted it with a ring twisting machine at different levels of twist, ranging from 100 to 650. We then took that twisted fiber and then we turned it into the yarn by turning it in the opposite handedness, an S-handedness, at a similar range, ranging from 100 to 65. We then took microscopic images of these yarns and plugged them into MATLAB and assessed the geometries. This is what our data looks like. So it is a 3D plot. We have removed any outliers from the fit, and these are the standard deviations. So this may not be very insightful or show you any really intuition about this data. So let's look at each of the two axes. So if you look twist versus each of these, bias angle, spring index, fiber diameter, and pitch, you can see that the fiber diameter seems to be the only thing that significantly changes via twist. That's surprising because when you twist these fibers, they get shorter. They take up less length. So you would expect that that material would go somewhere and that the fiber diameter would increase significantly. But we just didn't see that. And we also expected from literature that this twist would affect the writhe, the spring index, the bias angle significantly via spring mechanics. We didn't see that, however. Instead, what we saw was that the writhe seemed to almost independently control the bias angle, the spring index, and the pitch of these muscles. So what does this mean? Well, this means a few things. It means that we can pretty much control the geometry just with one factor, whereas the twist is related to energy in the system in all of literature. So we could maximize energy by controlling mainly twist, and then we can optimize efficiency by controlling the geometry, because the geometry affects the stiffness of these yarns and how they might behave in a coiled setup. So this data will help us improve our understanding of yarn mechanics, as it seems to go against most of literature in textiles and these artificial muscles and in spring mechanics. It'll help us independently control the fiber twist and the yarn geometry. So we don't have to fully model the whole system. We can focus on each one at one time. And then finally, we can combine all this to optimize the energy density and thus the efficiency of our artificial muscles, which will reduce the battery weight for the end user and the cost of the end device application. Now, that's the end of my talk. I'd like to acknowledge my funding sources, my T32 fellowship with the NINDS, the Electrical and Computer Engineering Department for its funding during the pandemic, the VPR over here at U of U, BlackRock Neurotech for providing a lab space during the pandemic, a graduate assistant who came and visited this fall, Johannes Mersch, and several of my undergraduate assistants who have been very, very helpful. I also need to disclose that my PI, Florian Salzbacher, has a declared financial interest in BlackRock Microsystems. Thank you for your time. I'll take any questions. Yeah, Jake.
Can you talk a little bit more about how you implemented the computer vision to figure out some of that?
Yeah. So I have backup slides because that doesn't show everything. Yeah, so I manually selected the region of interest. I then used MATLAB to identify the lower band of the region of interest and the upper band. And at each stage, I would then select the divot here and here and on the upper side. I can measure the distance between those divots in the vertical axis and horizontal axis. You may notice that there's a black region because these have been shifted to be linear. And in terms of geometry, we can measure the pitch and the bias angle by measuring, or we can measure the bias angle, the spring index, and the pitch from those different factors. And I can explain it as such. So the pitch is defined as this geometric relationship, and the fiber height, which is not the equal to diameter, is defined as this relationship. If you have a single helical coil, it's the point where they equal. If you have a triple helical coil, it's a factor of 3 difference. So let's just have a factor of pi, or the number of helices. And that's how we get to that measurement.
Great, thanks.
Yep. Yes, Hunter.
Can you explain a little bit more just how these flows are incorporated or would be incorporated into the prosthetic?
Yeah, so of course that takes a little bit of thought, and we aren't all the way there yet. But right now we form our yarns and we tie them to washers. So in terms of mounting them to a prosthetic, we're thinking of mounting them with traditional fasteners such as bolts, screws, nuts. Yes, yes. So when we've talked to manufacturers, the major advantage isn't that they're an artificial muscle, but that it makes their design problem easier. So it's a lot easier to copy something than to invent from scratch and to try to fit bulky, awkwardly shaped motors that don't work like human muscles into the anatomy of a human hand, instead of the whole human forearm, which is what we work with. Yeah.
Sort of similar to that, how do these yarns compare to like actual muscle in terms of like their ability to contract, the speed at which they contract, and
Yeah, so I study these artificial muscles because they've already biomechanically surpassed human muscle. They can exert more force per area. They can contract further. The problem right now is the temperature range. So that's why I've talked about efficiency so much, because I want to increase the efficiency to reduce the temperature range. So right now we're working between 20 degrees Celsius and 150. So that's not acceptable for an end-use prosthetic. So what we're trying to bring it down to is the human body temperature range of 33.2 C to 38.2 C. In terms of speed of actuation, like you asked, that depends on the scale at which you make them. Smaller things heat up and cool down quicker. So the scale is an important factor here. Literature seems to say that things are scale invariant. This is one of those instances where they aren't. So speed and time aren't scale invariant. But there's an ideal scale and an ideal wire gauge as well to heat it up internally through resistive heating. I think you had a question? Yeah, okay. Any other questions? All right, thank you.